Chebyshev's rule is a great starting point because it can apply to any distribution of observations. But it's really limited because it's a rule that is going to apply to any number of observations and any type of distribution. So we really would like to have a better rule that can extend a little bit beyond, just coming up with a few of these applications or a few of these generalizations of at least and at most. I'd rather be able to know pretty exact. So here's where we have the empirical rule, which is a much stronger rule, but it only applies to distributions that are approximately normal. So that they're symmetric, they're mound-shaped, they have that nice bell-looking curve. If you can make an assumption of these observations coming from a distribution that's approximately normal, then if you go one standard deviation, you're going to get pretty much exactly 68% or 0.68. If you go two standard deviations, you're going to be approximately 95% or 0.95. And then three standard deviations is going to take you to 0.997 or 99.7%. This is much more powerful because here it's still approximate, but it's very, very close. We're not talking about an at most or at least kind of value here. It's it's approximately 68%. That's the value that we get. So how do we use this empirical rule? Well, we can use it to check whether or not a distribution is normal. If you apply, if you look at the percent of data between 1, 2, and 3 standard deviations away, if it's close to the 68, 95, 99.7 rule, then that can tell you that your distribution is likely normal. You can also use this to describe a population. So you can help describe kind of your percentiles that are in this distribution. And if your population is approximately normal, then we know that it's going to be very unusual to see something more than 3 standard deviations from the mean. Most of your data, 99.7% of it's going to be within 3 standard deviations. So 0.3% of the time you are beyond that, which is really unlikely. So here are 3 pictures of the empirical rule. So you see if we go out 1 standard deviation, we hit 68%. If we go out 2 standard deviations, we hit 95%. And if we go out 3 standard deviations, we hit 99.7% or 0.97. Now, I like to adjust this picture a little bit and put it all together and split it up a little bit more specifically. So I'm going to add this to your notes. This is not in the textbook, but for me, it makes this calculation a lot easier to do. I'm going to start by drawing a line here at our mean. Now, if we go out 1 standard deviation on both sides, so we subtract the standard deviation and we add the standard deviation, I guess we are using S's right now. Then instead of saying that there's 68% here, I'm going to split that up into the 2 pieces. So really it's 34% is from the mean down 1 standard deviation and 34% is from the mean up 1 standard deviation. Because I do know that this one's symmetrical. I didn't know that for the Chebyshev rule. We didn't know that it was symmetric. Now if I go out 2 standard deviations, so x bar minus 2s and x bar plus 2s, here I get 95%. But what that means is I've now picked up an additional 27%. 95 minus 68 is 27%. So from this 27%, I can split that in half. That means 13.5% and 13.5% are going to be between that 1 standard deviation and 2 standard deviations. And likewise, if I go out 3 standard deviations, then I end up with 99.7%, which is an additional 4.7, and I can split that to get 2.35%. And then the very last little bit what's left over, 0.15% and 0.15%. So I like to refer to this when I'm looking at different values because it does just split this up a little bit more, and we can answer more specific questions. So let's actually look at an example here where we want to describe some speeding tickets. So this is from a random sample of tickets in Alberta, Canada in July 2018. And we can assume that these are approximately normal with a mean of 130 and a standard deviation of 25. And these are in Canadian dollars. So the first question, what proportion is between 80 and 180? So the first thing that I do is I plot the mean, so 130, and then I just go ahead and add my standard deviations. I'm adding 205 and, I'm adding 25 and subtracting 25. And then I've got, my little puzzle pieces. And if we want to know between 80 and 180, then I'm looking at from here up to here, which is 2 standard deviations. So I could just say, all right, it's 2 standard deviations, that's 95%, or I can add up my puzzle pieces. You add those 4 pieces together and you get 95%. Now, what if we wanted to be greater than 205 or less than 55? Well, let's think about where those are. I'm looking greater than 205 or less than 55. So this is the beyond 99.7%. So you could do 100 minus the 99.7% and get 0.3%, or you could just add these pieces are each 0.15% and we can add those together. If we wanted to know just greater than 205, then that's where I find it easier to have this table because we can just say 0.15%. And then the last question here, we want to be between 105 and 180. And this is another one where it's not a symmetric piece. We're not 1 standard deviation, we're not 2 standard deviations. We are, the 34, and the 13.5. So I'll add that up. And that's going to give me 81.5%. Now pay attention when you are giving your answers. If it's asking for a percent, leave it as a percent. If we needed to go into a proportion or a decimal, we can just divide by 100 to get 0.95, divide by 100 to get 0.003, divide by 100 to get 0.0015, and divide by 100 to get 0.815. So depending on the context, do you need to have a percent or a decimal? Here you've got the percents in the table. You can divide by 100 to get a decimal.